Some of you may have noticed that actually the title of this talk has changed from what it was originally 6 months ago. But rest assured, some of the information that would have been in that talk will be contained here, but this covers a little bit more. Since this report has come out, and I can show it to you, and Joan Parker assures me that this will be in the library soon. We didn't say what soon meant, but this is a report. It's called Sea Level Rise for the Coasts of California, Oregon, and Washington, Past, Present, and Future. And I'm a little biased, but I highly recommend this. Of course, I did contribute to it, but in any case, I will say that I have drawn liberally from this document in some of the slides that I'll show you. Basically, the talk is broken down into three parts. The first part deals with global sea level rise. The second part deals with regional sea level rise with particular emphasis on the US West Coast. And the last part, if we have time, deals with my own current research dealing with sea level acceleration and how we measure it. Okay. This was on the cover of National Geographic about, I think it was May of 2011. And it dealt with what's happening in Bangladesh due to sea level rise. As you know, Bangladesh is really a very low-lying country next to India. And people are now in the process of being moved from the low-lying areas to higher ground. And it's causing a real problem there. But I think the point I want to make here is the fact that this sea level rise problem is not something that's down the road. It's here and now. It's happening in different parts of the world, even though we're not directly affected right here locally. The impact of sea level rise, this is a short list, I can assure you, but I'll just go through these very quickly. Island nations in the mid-Pacific, such as Tuvalu, are starting to submerge, and plans, this is old, this is not current, plans for evacuation are underway. I think evacuation is already happening. It's more than plans at this point. Additional impacts include inundation and displacement of coastal wetlands, increased vulnerability to coastal storm damage and flooding. Shoreline erosion will be exacerbated, of course. Extensive damage to man-made structures along coastlines will occur. I think you heard about some of this probably from Gary Griggs a few weeks ago. I'm not going to dwell on this, but I'll just mention a few of the impacts here. Increased saltwater intrusion in estuaries and freshwater aquifers, altered tidal ranges in rivers and bays, changes in sedimentation patterns, and decreased light penetration for benthic organisms. Here's a figure taken from the NAS report that I just referred to. This shows an inundation map for the area just south of San Francisco on the peninsula. And this area here and this area here are actually underwater. Here, this map was created for an increase in sea level of 40 centimeters. That's between a foot and a foot and a half. So that's really not a whole big rise in sea level, but the airport in particular is very close to sea level. And I understand that actually work is now underway to actually shore up some of the areas around the airport right now as we speak. So that's from the report. It's in the first few pages. Background. Now let's turn to what's happening with global sea level as it stands now. I've tried to make this as up to date as I could based on the latest references. But by way of history, over the past 1,000 years and prior to the mid-19th century, average global sea level rise was on the order of 0.2 of a millimeter or less, which is pretty close to zero. During the mid-1800s, sea level began to increase, a change that's been attributed to the Industrial Revolution. There was a major increase in carbon dioxide in the atmosphere at that point in time. Global sea level increased at a rate of 1 to 2 millimeters per year during most of the 20th century, with higher rates observed since the 1990s. I'm going to talk about that several times during the presentation. Overall, global mean sea level has risen by approximately 20 centimeters over the past century. Rates of sea level rise have been estimated primarily from tide gauge data at various locations around the world, but mostly from Europe and the US, with very little data from the southern hemisphere until just a few decades ago. Until recently, tide gauge data was our only source of information on sea level rise. However, as most of you know, tide gauges are subject to platform motion due to tectonic effects, glacial rebound, and local subsidence and uplift. And of course, this is a major problem. Enter satellite altimetry. This is something relatively new. We've had satellite altimeter data to look at sea level rise since the early 1990s. And this has really changed our knowledge base about sea level around the globe tremendously since the advent of altimetric data. Let me just say a few details. For those of you who may not be familiar with altimeters, they are essentially an active radar system, and they measure the distance between the satellite and the ocean surface by measuring the time required for a radar pulse to reach the surface and be reflected back to the satellite. It's very much in principle like the echo sounder aboard a ship. However, extensive signal processing and many corrections have to be applied to the data before sea levels per se can be actually extracted. We use tide gauge records to calibrate the altimeter data, and that's a problem in itself because we have to trust the tide gauge records. If the tide gauge is sinking or uplifting, and we're not aware of that, then of course the calibration is going to be suspect, and that's a serious problem. That's a whole field in itself. Altimeters, the real boon here is the fact that altimeters provide sea level data on a global basis, helping to fill in the gaps in coverage from the sparse network of tide gauges. A little more background here. Based on the satellite altimeter data from Topex Poseidon and the most recent tide gauge data, estimates on the rates of sea level rise since the early 1990s are now very close to 3 millimeters per year. This is quite a change from most of the 20th century where the rates were usually quoted to be less than 2 millimeters per year. So we've had a very significant increase here over the last 20 years. The question often comes up is the rate at which sea level rising, is it accelerating? And the bottom line is that we've measured very small rates of acceleration. And this is not compatible with the projections that we're making, because if the projections are correct, we should be observing far more acceleration than we see. So there is a problem here. Sea level rise is primarily due to thermal expansion of the oceans and the melting of glaciers and ice sheets. The last, we refer to that as a cryospheric or a freshwater contribution. Both are related to global warming. And one of the problems, the relative contributions of thermal expansion and the cryospheric contribution, the estimates of their relative contributions really vary tremendously. And I'm afraid to even quote numbers like 50-50 from each, because it depends on the reference that you look at. The numbers vary really widely. Here is a list of most of the factors that are affecting relative sea level rise. And I have put the word relative in italics here because when we talk about relative sea level, we're talking about sea level that we measure from a tide gauge. Now, if the tide gauge is on a platform that is moving up and down because of tectonic effects, then we truly are measuring relative sea level relative to the platform on which it's measured. But it's not absolute sea level rise. So we need to keep that distinction in mind at all times. You can see this for yourself, the list of factors that affect sea level. The melting of glaciers and ice caps and ice sheets, of course. These numbers here are subject to change, and these are not up to date. The one figure that is up to date is the thermal expansion is considered to be around 0.4 or 0.5 millimeters per year. The big question is this terrestrial storage. For a long time that was ignored, and now that deals with reservoirs and aquifers and things like this around the world. We now realize this may be a really major factor. This number is definitely not correct. In fact, in the Naas report here, our current one, we've said that actually sources and sinks of fresh water on land tend to balance. And so we've treated this particular contribution as being essentially in balance, so it's zero. And that's what we've done in the Naas report. And then we have oceanographic processes, which I'll talk about. We have isostatic effects, and we have local subsidence and uplift, which are all variable and usually unknown. Okay. The enigma of 20th century sea level rise. This is a phrase that I think Walter Munk came up with maybe about 15 years ago. The problem is that the values that we showed on the previous slide, if you add all those numbers up, you don't get the numbers that we get when we go out there and we measure sea level rise based on tide gauges and altimeter data. It turns out that the estimates of sea level rise obtained from tide gauges and altimetry give significantly larger values than those obtained by estimating the contributing factors separately. There's a big difference here, and this gives rise to the so-called Enigma, and sometimes it's called the attribution problem. The uncertainty associated with terrestrial storage may contribute to this difference. Also, our expectations are that as other measurement uncertainties are reduced, the difference is expected to become smaller. I'm particularly interested in this particular one. This is from folks in Australia. These are two globally averaged records of sea level. In both cases, over 1,000 different tide gauge records were averaged using a fairly sophisticated method of averaging, which I won't go into. But these are the kinds of plots you get, the graphs you get when you average many tide gauge records together. And these are both produced by CSIRO in Australia. They're very similar, but they were produced slightly differently. What I want to point out here is some of the features that these globally averaged records of sea level have in common. Not only these two here, but other ones that have been globally averaged as well by other organizations. What we see here in the 1920s and between 1920 and 30 is what they refer to in the literature as an inflection point. And this is very directly traceable to changes in ocean thermal structure, upper ocean thermal structure. When you look at the two side by side, if I had time, I'd show you because I have all the data in the plots. And you can see very clearly that the two are closely related. When you go further up the record here, you look in this period between 1960 and 1970. There's another inflection point that's often discussed in the literature. This is attributed to a volcanic eruption, Mount Agung from Indonesia in 1963. Of course, when these volcanoes kick off, they emit a lot of aerosols into the atmosphere. And of course, this reflects back a lot of the incoming solar radiation. So for a period of a year or two after these eruptions, we get some cooling of the ocean surface. That's well known and well documented. However, as I look very carefully at the ocean thermal structure, globally average sea surface temperature, I also see that this could be related, this one here, I'm sorry, right here, could be related, at least in part, to changes in ocean thermal structure. There's one final inflection point up here during the 80s, which I believe is related to the El Chichon eruption back in 1982. But something else I'll say about these globally averaged records, these here tend to preserve the major El Nino signals. The phase associated with the El Nino signals around the globe tends to be phase coherent, and so they show up in these averaged records. However, one of the blessings is the fact that a lot of the oscillations that are problematic, particularly decadal oscillations and even longer period oscillations, tend to get averaged out because they are not phase coherent, and so they tend to cancel. And so when I looked at the power spectrum of these two records, there are no peaks at all that are significant whatsoever. So one of the really good features of this averaging is the fact that these oscillations, which tend to, in some ways, contaminate the information, are averaged out. Okay, moving on. Okay, this is a plot from the NAS report. And this is global sea level rise for 3 forecast horizons, 2030, 2050, and 2100. And we can talk more about how these were produced a little later on when we start talking about the models and that sort of thing. But what we see here, this is the results of the global sea level rise. Shortly, we'll talk about what happens here along the West Coast, which is somewhat different. But in any case, we can see here, we take a central value here for 2030, and we get something less than 20 centimeter rise by the year 2030. You can see what the uncertainty is in terms of the width of the bar. I think this is kind of a nice way to plot it. It's very easy to follow. The second forecast horizon at 2050 is here, and a central value here would be somewhere around 30 centimeters by 2050. And down here at 2100, a central value would be somewhere close to 100 centimeters. Now, the green curves are based on a very popular semi-empirical model, and I'll say more about that in a few minutes. The blue curve, however, is from the last IPCC report. And of course, the thing that jumps out here is the fact that look at the increase in projected sea level 5 years after this report was put out based on the latest information we have. So this is something that seems to be, you always see it. As soon as you see a new projection, it always projects higher sea levels than what we've seen previous to that. But this is from the report, and let's talk about regional sea level rise. Turn to regional sea level rise now, and what's going on regionally. Regional sea level rise is not uniform around the world. Although sea level is rising in many areas, in some areas it is falling. The west coast of North America is a good example of where regional sea level rise is quite different from global sea level rise. Based on altimeter data since 1993, the rates of sea level change appear to be negative along the west coast, consistent with recent tide gauge data from San Francisco. Now this last bullet here I've taken right from the report. It says, from the report we said that relative sea level rise along the US west coast differs from the global mean because of local thermosteric contributions. By thermosteric we mean the thermal expansion contribution. Dynamic height differences caused primarily by changes in the winds, the gravitational attraction of glaciated land masses, and vertical land motion. I would make a comment about the gravitational attraction of glaciated land masses. This is mainly due to the glaciers in Alaska, and I'll have more to say about that in just a few minutes. Okay, here's one slide that really turns me on. And that is, this shows what we got from altimetry over a 15-year period between 1993 and 2008. And I draw your attention to the scale down here. These are rates down here, millimeters per year, and contoured, as you can see here. The very reds and whites up here indicate rates of sea level rise approaching 10 millimeters per year. Now, earlier I mentioned the island nation of Tuvalu. Tuvalu is somewhere out in this area right in here. And other island nations in the same region are being affected the same way. Guam is really having serious problems now. They're trying to build a new Navy base there, and they're having very serious problems with sea level rise. Now, conversely, look what's going on along the west coast of North America and even part of South America. We see rates of not sea level rise, but actually sea level decrease along our coast. And the numbers down here you can get off the graph, not off the scale, but it's not precise, but you can see it's probably at least a negative 1 millimeter or maybe even high as 2 millimeters per year decrease in sea level. Now remember, this is only a 15-year period between 1993 and 2008, but still, you'll see that this is very consistent with what we see in the tide gauge record from San Francisco. I'll show that in just a few minutes. But this is a very revealing slide, in my view. Other recent advances that we'll talk about here. One is global positioning systems, GPS. We thought this was going to be a panacea for the problems we've had with local subsidence and uplift in the vicinity of many tide gauges, but as you'll see, that's not really the case. You know, it's often the case that the closer you look, the more complicated it gets, and this is a prime example. The second advance, which you may not be familiar with, but really is kind of exciting, is this Gravity Recovery and Climate Experiment satellite. It's called GRACE. This changes in gravity can be used to map changes in the distribution of mass in the ocean, and thus to better understand what is causing sea level to change. The system is very clever. It's a 2-satellite system, and basically the way this works is the fact that changes in the distance between the 2 satellites are directly related to changes in the field of gravity of the Earth. And so by keeping constant tabs on the separation between the 2 satellites, they come up with a direct measure of the Earth's gravity field. And the real beauty of this is the fact that it's much more accurate than anything we've had in the past. In fact, just a few more words on this. The whole mission is under JPL management. Right here, the mass of gravity are up to 1,000 times more accurate than anything we've had in the past. So it's really a big step forward. And further down here, measurements from GRACE have shown how the thinning ice packs associated with glaciers affect sea level in surrounding areas. As a case in point, these data suggest that weaker gravitational attraction between a thinning Alaskan ice pack and waters off the US West Coast may be contributing to a latitude-dependent change in sea level. And we're observing that. And it can be directly accounted for by changes in the ice pack. Yeah.
So what that's saying is that the ice is going away, so the land is kind of rebounding, coming up. Ice is static,
right.
It's causing more gravity to
Yeah, there's less ice, there's less gravitational attraction. So the pull of gravity on the water nearest the ice pack, of course, is affected the most dramatically. But this is a really quite new stuff. This whole realization about the importance of the gravitational attraction between the glaciers and the surrounding ocean is something that's only, It was understood in theory, but actually really putting some numbers on this is something that's relatively new. This is some of my own work in contributing to this NAS report. My responsibility, one of them, was to actually analyze the data from 28 tide gauges up and down the U.S. West Coast and apply GPS corrections to all of these records. And this is from Crescent City, which is in Northern California. And this is the original record. And when we fit a straight line to this, as is normally done, when we look at rates of sea level rise, we simply fit a straight line to the data using least squares regression, and we estimate that we take the slope from that, and that's the number that we present. It seems simplistic, but that's what's done, and that's what's been done ever since day one. In any case, you can see here from the original data, the slope is close to -1 millimeter per year negative slope here. Now, I applied the GPS corrections that were applied to me from the University of Hawaii, and lo and behold, we came up with a positive slope of 1.44 millimeters per year. Now, I want to hasten to point out that in this case, we got a result that appears to be favorable if we think that sea level is rising in this location. However, in several other cases, actually a number of other cases, I got just the opposite result. I had cases where the sea level rise based on the record, the original data, looked reasonable, like 1.5 millimeters per year positive. And then I'd apply the GPS correction from the nearest GPS receiver, which might be less than 10 kilometers away from the actual tide gauge, and I'd get a negative slope. So what we've learned from this very painfully is the fact that the horizontal scales of vertical motion are extremely short in many, many cases. And so what we see 5 or say 10 or even 5 kilometers away from a tide gauge may be very different from the vertical motion that the tide gauge itself is experiencing. This really complicates matters. Of course, the obvious comment you would make is, well, why don't you put a GPS receiver on every single tide gauge? That's almost a no-brainer. And actually, that's starting to happen, but it seems to be kind of slow. I'll say a little bit more about that in just a few minutes. But it's a complicated problem because vertical motion, the horizontal scales of the vertical movement, are very short in many cases. Sure.
This goes back to before 1940.
Yeah, this one goes all the way back to almost 1930.
But the GPS obviously doesn't go back that
Right. Very good question. And that's something a lot of people, actually we have at least 2 papers that we can refer to from the people who really work on this, that the consensus seems to be that it's a reasonable thing to do to take a GPS record that shows a rather consistent slope, whether it be negative or positive, whatever the case may be, and extrapolate that back to the length of the tide gauge record. You can always say that that's not a good idea, but the people who have worked on this problem, I haven't worked on it directly myself, but I can quote at least 2 references where people have looked at this problem and seem to think it's a reasonable thing to do. Obviously, it is open to question. Definitely is open to question, but that's a very good question. Okay, a number of you have seen this. This is from Elkhorn Slough, from Eric Van Dyke several years ago. This is an old record now, but this is from his first GPS receiver in Elkhorn Slough. And you can see that the straight line slope here, it actually turns out to have a slope of about -1 millimeter per year. But as I've talked to other folks who worked with Eric over in Elkhorn Slough, other GPS receivers in Elkhorn Slough show quite different trends. And so this just supports what I just happened to say about the fact that the spatial scales, the horizontal scales of vertical motion can be very short. So what you see one location only a few kilometers away, it may be very different. It's a very serious problem. Okay, let's say a few words about the models that were used in the NAS report and that are generally used to predict future sea level. The basis is usually general circulation models of the atmosphere or the ocean, or now what are used extensively are called the coupled atmosphere-ocean models. And they've only really been perfected in the last 10 or 15 years, but it was a big challenge to actually couple the ocean and the atmosphere together. But now I think most people are very satisfied that they're working very well, and there must be at least 20 of them around the world now operating regularly. These models are based on physics and only predict a steric component of sea level rise. That's thermal expansion. And actually, I should point out that salinity does play a small role, but it's a very secondary role. Semi-empirical models are often used. They're becoming very popular. They're so much easier to use. They're so much simpler. You can run these on your own laptop. You don't have to use a supercomputer. These models employ empirical relationships between sea level and other variables that can be predicted with greater accuracy. And global mean temperature is one of those that can be predicted with greater accuracy. They predict asteric and land ice or cryospheric contributions together but contain no physics. Strictly empirical models are often used now to predict the cryospheric contribution to sea level rise. And we actually used a strictly empirical model for the cryospheric contribution to sea level rise in the NAS report. Okay, this shows the projections of global sea level rise from 17 different AOGCMs around the world. And these calculations were done to support the IPCC report from 2007. So these are not current, but we use these in the NAS report because to produce these took years of work and probably millions of dollars to produce. And so these are not produced overnight. But in any case, they're very revealing. What we see here, when you look at these are projections now from 2000 to 2100. And you can see that this is done for 17 different models and also for 3 different greenhouse gas emission scenarios. We have to input in these GCM models, we have to tell it what the atmosphere is going to do, what's going to happen to CO2 and other greenhouse gases. That's not a model output, that's a model input. And we don't have control over that. And these models come under a lot of criticism because of all the variability between the models. There's a lot of variability there. The range of uncertainty is very large. But actually, what happens in the future with greenhouse gas emissions is going to depend a lot on policy and what happens with policy decisions that are made in different countries around the world. So modelers can't be held responsible for those kinds of uncertainties. But they're a fact of life. And in any case, we can see here the spread of uncertainties at 2030, and then we get out here to 2100. And the uncertainty is huge. And these make a very critical input to our final estimate of uncertainty in these forecasts. The differences between these models is really crucial to give us a handle on the uncertainty. Okay, this is now, we're talking about the US West Coast. And this is from the report. And this is a little different than what we showed before for the global projections. We actually have here the same forecast horizons, 2030, 2050, and 2100. The blue are for Oregon and Washington. The gold or yellow are for California. The red, of course, is a global, just included here for comparison's sake. And the green, again, is the semi-empirical model that we saw before. Again, that's a global prediction. Certain things were done here. For example, I should go back just for a second here. I might point out that this is just for the thermal expansion contribution. This doesn't include the cryosphere. So this is only one part of the story, but it's a very important part of the story. We broke the coast down into 2 regions for several reasons, but the projections are slightly different, as you can see. Oregon and Washington are a little lower generally than the projections for California. And part of that is due to the effect of the Alaskan glaciers. When that was taken into account, we started to see differences between the northern part of the US West Coast and the southern part. And the logical break point is Cape Mendocino. And so the geologists made a point about the fact that once we are north of Cape Mendocino, we're dealing with Cascadia. And once we're south of Cape Mendocino, we're dealing with St. Andreas. And so it's a very different situation. So that was a logical break point. And this is the way it turned out and the way it evolved. But in any case, as you look at these projections for 2030 now for Oregon and Washington, we're down somewhere between, we're less than 20 centimeter rise for the central value here. For California, it's a little bit higher. And as we go up to 2050, we see for Oregon and Washington, it may be close to 30 centimeter rise. For California, it might be closer to 40. As we go up to 2100 and we look at Oregon and Washington, we see, maybe somewhere around 80 centimeters. And when we look at the global one, this light seems to disappear once I get too far down. In any case, when you look at the gold curve for California, the central value there is somewhere around 100 centimeter rise that's projected for 2100. And it's significantly higher at that point than the projection for Oregon and Washington. But like I say, a large part of the differences are because of the gravitational attraction effects. But these are in the report. You can dig these out. You can see what the uncertainties here are really huge. I mean, look at the range of uncertainty here for the 2100 projections. A lot of that is due to the cryosphere, even though I showed you large uncertainties associated with the thermal expansion contribution. The uncertainties associated with the cryosphere are even larger. It's a very difficult problem trying to predict freshwater inputs to the ocean because there's so many factors involved. Okay, moving on. Now speaking locally here, I'm not going to dwell much on the San Francisco record because I've talked to this before on 2 previous seminars, but I will say a few things which I think are relevant to this particular talk. And one thing is the fact that the San Francisco record has been treated as a benchmark against which most other records along the West Coast have been compared with. Also, the tide gauge has moved from San Francisco to Sausalito in 1877 and then moved back to San Francisco in 1897. I'll say more about that in just a second. Like most tide gauge records, the closer we look at it, the more problems we find. Recent evidence points to the possibility that the platform on which the tide gauge is mounted has been subsiding for many years. A lot of people didn't want to hear about this, but we've looked at least a half a dozen different GPS receivers around the closest ones to the San Francisco tide gauge, and we see subsidence at almost every one of those. And subsidence on the order of maybe as high as 1 millimeter per year. Now, if you look at the overall slope for the San Francisco record, it's about plus 1.8 millimeters per year. If you subtract 1 millimeter per year due to subsidence, you're down to 0.8 millimeters per year actual rise, if we're correct. In any case, this will make a big difference if we actually get a handle on this and can put more accurate numbers on what this subsidence is all about. The one bright spot, the one bright spot is the fact that NOAA is now in the process of installing a GPS receiver within 1 kilometer of the San Francisco tide gauge, and I've been in touch with the guy who's doing the work. And I don't know if it's actually operational yet, but I think it's in place. It may not be operating, but it's in place, and that's a step in the right direction, clearly. I've shown you this before. Look at the bottom plot. This is a 2-way layout of the San Francisco record with a month on the vertical axis and a year on the horizontal axis. So you can see not only the long-term trend, but you can also see seasonal variations. And you can see here at a glance that during April and May, sea level is lowest along our coast. And then during the early fall, September and October, sea level tends to be the highest. But that's about all we can glean from this display here. We have to use other techniques to look at this in more detail. What I want to point out here is this little bump here. This has been something that has been elusive. No one's ever satisfactorily addressed where this hump comes from. It's centered around 1880, and that would make you think, I just mentioned the fact that the tide gauge has moved from San Francisco to Sausalito in 1877, and then it was moved back again in 1897. Well, then you say, well, could there be a connection? So we actually took a look at that. And I draw your attention to the top panel here. What I did is to actually take the monthly data and average the first 10 years before the tide gauge was moved, and then the 20-year period during which the tide gauge is located in Sausalito, and then average the 10 years following the move. And you do see a significant difference here. The difference on the forward side is about 2 centimeters, and the difference on this side is more like 3 or 4 centimeters. So you see this, and you say, okay, what's the explanation? Why is this happening? And looking at this particular figure that comes from the Army Corps of Engineers back in the 1960s, this shows, and the curve I want to draw your attention to is this one here called MTL. That stands for mean tide level. At the Golden Gate, that would be synonymous with mean sea level. But the point is, as we go from the Golden Gate and we move up to the Delta region, further up in northern San Francisco Bay, there is a gradient to sea level. The water is essentially going downhill. There's a hydraulic gradient here. And the actual value of this gradient is about 1 centimeter change in the vertical for each 3 kilometers of horizontal displacement as you go further north in San Francisco Bay. So using that figure as a correction, I used a figure of, actually, if you look at it, Sausalito is about 6 kilometers north of San Francisco. So with a gradient of 1 centimeter per 3 kilometers, you get 2 kilometer difference between San Francisco and Sausalito. And if we apply, and that's just about the figure I had here, it's very close to 2 centimeters based on observed data. So when I made that correction of 2 centimeters, this is the curve I got in red down here versus the blue, which is the original hump that we had in the data before I made that correction. Well, I think you'll agree, it certainly hasn't removed the hump completely, but it's made a change in the right direction. It's certainly reduced it to some extent, and now we understand where that came from. So we were kind of pleased with that. Every now and then you jump into something that just turns out to be right. At least we think it is. We hope it is. Now something is current. I referred to this earlier about what's going on in San Francisco in terms of what's happening in the last, say, 20 or 30 years. Based on the record from San Francisco, I think you'd all agree that we certainly don't see it, that sea level is increasing dramatically here. In fact, since the late 90s, it looked like it might even be decreasing slightly. Of course, this is subject to how you do the smoothing, and you can use different smoothing operators and come up with slightly different curves. But none will show that sea level is increasing dramatically during the last 20 or 30 years. In fact, most people say right now it really hasn't changed much in 30 years since about the early 1980s. And so the real issue is, why is this happening? What's going on? And that's what some of my current work is involved in. Why is sea level decreasing? And this is very closely tied to the fact that temperatures are decreasing at the same time. This figure here was taken from a paper that was published in the last 2 years by Garcia, Reyes, and Largier. And they looked at buoy data along the west coast from Oregon all the way down to Southern California. On this left panel, they plotted temperature. Actually, sea surface temperature is the light curve, and then the dark curve are the longshore upwelling favorable winds. And they both show that since 1982 through 2008, that sea surface temperatures have decreased over this period, and the longshore winds have increased. I probably should have turned that around, since the colder temperatures are due to the fact that the winds have become stronger. But in any case, on the right, we have the upwelling index, which is often used as another measure of upwelling intensity. But in any case, when I looked at this, and let me say one thing here, I've looked at some of the same data, not as extensively all the way as far south or as far north, but I've looked at 3 or 4 different locations in Central California. And what I found was the fact that, yes, if you did look over the entire period from 82 to 2008, there were the changes that are showed here, but the real cooling and the real lowering of sea level has really happened since the last major El Nino, since 1997-98. Actually, between 82 and 1997 or 8, temperatures have actually increased very slightly, but they've decreased dramatically since that El Nino over the last 13 years. There's been a really major decrease in surface temperature. So the explanation that's given in this paper is based on an argument by Andy Bakken that was published in Science back in 1990. And he stated that due to global warming, that inland coastal temperatures would increase due to global warming, as they have. And that, of course, the thermal lows in the atmospheric pressure domain will correspondingly decrease as the temperatures increase. So you get a thermal low inland. And of course, what's driving the longshore winds along the coast here is the pressure gradient between the thermal low inland and the subtropical high pressure system offshore. So if you intensify the thermal low inland, the onshore-offshore pressure gradient gets stronger. And that's what drives the longshore winds. And that's the argument that Garcia, Reyes, and Largier referred to based on the Bakken paper. Now, more recently, another paper is coming out by the folks from Scripps, Bromersky, and his colleagues. And they agree that the longshore wind stress has intensified. And along with that, the offshore, the wind stress curl is intensified, which they go hand in hand. And so when you have greater wind stress curl, you have greater offshore Ekman transport. That brings up the cold waters and lower sea levels. So that all is a consistent scenario. But they attribute the stronger winds to an intensification of the Hadley circulation offshore, which is a major circulation system in the Central Pacific. And they say that the influence of the intensification of this circulation pattern extends all the way to the coast. Now, they don't say, they haven't proved this, but they suggest that this could be the explanation. Well, I toss out a third possibility, and this is the basis of a proposal I submitted a few months ago. And when I looked at temperatures off the central California coast, one thing I did not mention is the fact that I broke it down by season. In fact, I broke it down by month. And what I found was the fact that there's greater cooling in the winter months than there is in the summertime. This came as a real surprise to me, and it's certainly contrary to conventional wisdom, because everything seems to be tied to upwelling or the lack thereof. Whereas what I'm seeing is more cooling in the winter than I am in the summer. And as I thought about this, I also remembered a paper that came out, and I forget the journal, but in any case, I went back and read it carefully. And it's a classic paper that talks about the fact that winter storms in the Northeast Pacific have increased both in frequency and intensity, particularly intensity, since the mid-1950s. And that increase continues right up through the present time. And these storms cool the upper ocean due to sensible and latent heat transfer and very intense wind mixing. And so if we have more storms and they're more intense, we get more cooling due to winter storm activity. And so I'm proposing that this may be one of the explanations. It may not be the only explanation, but it may be an important explanation for why we are seeing continued decreases in coastal temperatures and sea level. In any case, I'm working with a colleague from NCAR to use an AOGCM to see if we can test all of these possibilities to really try to sort this out and understand what's really going on. Almost done here. Sea level acceleration. What is it and who cares? Sea level acceleration, I told you I'd get back to this early in the talk. Sea level acceleration measures the change in the rate at which sea level is rising. Typically, the way this is calculated is simply to fit a second degree polynomial to the record. Second degree is important because that captures the curvature. This term right here captures the curvature. And so you fit a second degree polynomial to this sea level record, and what you're looking for is this coefficient right here, C. So you solve for that, and that is what is published in all the literature as of today for rates of acceleration. And it's usually expressed in millimeters per year squared. Most of the accelerations that have been measured and published, including a few of my own, are very small. They're close to zero. We expect larger values based on the projections, but we're not seeing them. So the question is, why are we not observing increased rates of acceleration? In any case, I don't have an answer for that yet, but at least I'm working on the problem. Here's fitting polynomials to the San Francisco record. If you fit a polynomial, second degree, to the entire record, you get this red curve, which shows positive curvature. That means you have positive acceleration with a number which is quite small, but it's positive. That's the point. Now, if I start the fit in 1900 instead of 1855 and fit just the last, say, 110 years, this is almost a straight line. There's almost no curvature here, and we get almost no acceleration at all between 1900 and 2011. Now, if we make the period even shorter, starting in 1925, we actually get negative deceleration. And I think by now you can guess why that is, because during the last 20 or 30 years, we haven't seen much increase in sea level. So it really affects the curvature of the record. But in any case, this is how sea level acceleration has been measured up to now. However, there's been a very serious problem in estimating acceleration. The present method of estimating acceleration cannot distinguish between apparent accelerations which arise from decadal and longer scale oscillations in sea level and the true underlying acceleration that would be measured if the oscillations were not present. And everybody who has worked on the problem complains about this issue. Everybody recognizes it. They know it's a big problem. And so what we have done is to get around this problem is to use empirical mode decomposition, which I've discussed in previous seminars, but it's a method of decomposing a time series into orthogonal modes, and each mode tells part of the story. The trick is to interpret these modes correctly. But in any case, what we can do by doing this is to separate out the modes, and those modes which contain the oscillations can be thrown out, and what we wind up with is a residual, which is really the long-term trend, but it has no influence from the oscillations that are buried in the record. And so they're relegated to lower modes and they're isolated from the residual. So what we do is extract the residual and we analyze that separately. And here's the result that we included in our paper. The top plot is actually the residual applied to the entire record at San Francisco. This is the displacement, if you will, of sea level. And then the second plot is the first difference, the first derivative, if you will, and that shows the rate of change of sea level. And you can see the numbers vary over the length of record here from less than 0.5 to almost 2 millimeters per year. And what we do to get a single number is to simply average this curve and get a single number from it. And it actually agrees rather closely with values that have been published using other techniques. The last curve down here, this is the acceleration. This is the second derivative, and we actually the range over here is rather small. And again, we average this whole curve to get a single global value for acceleration. And as it turns out, the numbers we got for acceleration are rather close to the values that have been published using the standard conventional approach to estimating acceleration. That we found reasonably gratifying. We're using a different technique, so there's no reason why it has to match exactly. But I think we might be concerned if they were vastly different. But in any case, this is a different approach to looking at acceleration. We're kind of excited about it, and we think it's really got some potential. Closing comments, we're almost there. Compared to thermal expansion, the processes that affect the cryosphere are poorly understood, making this component much harder to predict. And I don't think there's anybody who worked on the cryospheric parts of this NAS report that would disagree with that statement. I think they all recognize how difficult it is to work with these ice sheets, glaciers, and all those various difficult to quantify factors. Each time new estimates of global or regional sea level rise are published, they invariably exceed the previous values. And I wonder when this is going to start to end. The models indicate that absolute sea level rise along the west coast is quite uniform. However, there will be significant differences in relative sea level rise due to the local subsidence and uplift. And that's, of course, what we measure with a tide gauge. If feedback processes are found to be important in maintaining strong upwelling favorable winds along the west coast, and that was the first hypothesis I talked about, the Bakken hypothesis, that would favor this sort of a feedback process. They could offset sea level rise for some time to come. And that might be contrary to what we have in this report at some future time. That remains to be seen. Much of the uncertainty in model projections is due to the assumptions about greenhouse gas emissions that are required model inputs. And I already talked about this just a few minutes ago. But these greenhouse gas emission scenarios are model inputs. They're not outputs. And the model performance itself has nothing to do with these. These are inputs. And so the criticisms that these models come under constantly for having such a huge uncertainty in the forecast is at least in part due to the fact that we don't know what these greenhouse gas emissions are going to be, and we have no control over that. Okay, the final comment I would make here is that GPS data, rather than being a panacea for estimating sea level rise accurately, has been problematic due to the excessively short spatial scales of variability associated with vertical ground motion that are frequently observed. And that's getting to be a very serious issue. I think most of us now who are working in this area realize this is an issue, and it just means that we need information on ground motion closer to the tide gauges, and I think that's going to happen. Good place to stop. Thank you. Maybe a few questions. Sure. Right.
You said that there was a dearth of tide gauges? So
No, that was a different comment. The dearth of tide gauges?
right, so how do you calibrate altimetry if there are no tide gauges?
That dearth comment referred to tide gauges in the southern hemisphere. Until the last few decades, Australia has a few tide gauges, but most of South America and Africa has virtually no tide gauges. And when you're looking at a global issue here, you need tide gauges distributed rather uniformly around the planet, and we don't have that. Most of the data comes from the US and comes from Europe. And the really long tide gauge records all come from Europe. Those are the ones that are really interesting. There's a lot of goodies you can pick out of those records from Stockholm and Brest, France, and some of these other places. They go back to the 1700s. But Your question was about the dearth of information in the southern hemisphere. It's very true, but they're starting to rectify that problem with more tide gauges now. The calibration deals with just being careful about any tide gauge that we pick to use as a calibration benchmark. We want to be careful that that tide gauge is not subject to vertical land motion that we're unaware of. And so a lot of care is exercised in picking tide gauges that we think are reliable and are not subject to tectonic effects. Yes, Leslie.
I wanted to ask you about another effect on sea level in addition to the cryospheric and the atmospheric, and that's changes in sea level slope. So, you know, in particular, you know, in
The one
combination with the, if you change the atmospheric forcing, you're changing the upwelling, you're also changing the strength of the barotropic geostrophic current, and so that's associated with sea level slope. What kind of contribution could that make, and is that included in?
What is included, and is truly a Pandora's box, is the inverse barometer correction. And I think that's really what you're referring to.
Well, no, I'm not. That's another one, though.
Well, I could have opened up that Pandora's box here and we could have tied up a half hour getting into the problems with the inverse barometer correction. Everybody wants a simple equation. Just give me the equation, I'll apply the correction, and let's forget about it. But it's not that simple. There's all kinds of spatial scales of variability that are ignored when you make that kind of a correction to the inverse barometer issue. But
What I was really asking about was the change in the strength of currents and the associated change in the sea level slope.
yeah, well, that ties into what I said about some of the factors that are affecting sea level, we think, in the last 20 or 30 years. The fact that the winds are changing, they're becoming more intense. And the question is that a coastal effect that may be driven by changes in the onshore-offshore pressure gradient? And or is that related to a larger scale process further off the coast, as the folks from Scripps seem to think it is, related to the Hadley circulation? I kind of like the one that, the Bakken argument myself, but nobody's proven it. The point is nobody has shown that that is actually true. And so I'm trying to stir up the pot here and say there's even a third possibility here that may be a factor in causing sea levels to get lower and temperatures to go down. And so we're hoping that an AOGCM will actually shed some light on that and maybe sort this out. Erica.
So all three of those arguments are all atmospheric forcing, and we are an eastern boundary current. And what I don't quite understand, I was surprised when this report came out because I don't understand if municipal managers on this coast are getting this story at all. They're sort of getting, you know, the difference between what East Coast cities are going to experience versus cities on the West Coast is dramatic, and it has everything to do with the temperature of the water. We're an upwelling coast, plus our water's getting pushed offshore all the time, and that is the way our system works. I'm concerned that that story, you know, regardless of what exact physics causes it, I think the rest of the world doesn't care about what we physical oceanographers come up with. I think they're not getting the basic story that the circulation physics of an eastern boundary current are such that we're not going to get as much sea level rise here in California and Washington and Oregon as the East Coast. What do you think that your group adequately represented that story in this report?
No, I don't, and I was one of the few that beat the drum to say we should talk more about this. Because if it turns out that the Bakken hypothesis is correct, that is a feedback mechanism that could be in place for a long time. And that will continue to keep sea level lower along the coast here. And I think that's a definite possibility, and I wanted to see that discussed in the report. And it's really shortchanged, there's no question about it, because they want to see, everybody says, well, in the long term, we're going to see sea levels like we see globally. And I'm not really convinced that that's true. And I must have said that at least a half a dozen times in various meetings, but I was...
Not making it up. I was at these meetings in Monterey with those municipal people. That story didn't get told at all.
Oh, I know.
I'm sitting here
Oh, I
going,
know.
how am I supposed to represent this as a scientist, because I go and give talks to those kind of crowds too, and I'm concerned. They're going to think that we're lying to them because you're giving them this idea that it's really bad news. Well, the West Coast might be protected from this bad news, and nobody else in the country, in the world.
I agree completely. I've said exactly the same thing in many different places here about that, but I was always outruled on that because they want to give what they think is going to happen in the long term, and they're thinking in the long term that actually things here will turn around and it'll be more like the rest of the globe. And I'm not convinced that that's really the case. And so I think it's a very open question, and I also dealt with this locally here. In fact, Mike, where's Mike? Mike. He's not here. But Mike was one of those who wanted to push the issue about the fact that, well, things are going to change. Things will come around here, and it'll be more like what's happening with global sea level rise. And this is the story that people wanted to hear. They think it would be, the logic behind pursuing that argument was the fact that it was a way of being safe and secure because, if things get worse, at least we're covered. But if things don't stay as they're staying right now, then, we could be in a situation where, we're not covered. So I agree with you, Eric, on this. And I've really talked about that in several different forums. And usually I get overruled on that. Nick, I was waiting for you. You've been strangely silent.
I missed because my eye focused in on the red hotspot, that summary global picture you had, and I just wondered, along the same line as Erica with regard to eastern boundary currents, are there any mirror patterns in northern and southern hemisphere?
Let's look. We could look at Northwest Africa and look at Northwest Africa. Actually, we don't see, well, we'd look over here and we don't see quite the same thing.
I see big blue on North and South America, which is a dampened millimeter per year sea level rise, even negative.
It's negative.
So
Sea level is going down based on the altimeter data since 1993.
So it's like a fair, Erica's generalization is that it is a sea level, depends where you sit in the eastern boundary current situation.
I agree with your arguments. I agree completely. But the overall thinking that I was exposed to, particularly with this committee, is the fact that things will tend to correct themselves. And this, what we might refer to as an imbalance here between the Western and Eastern Pacific, will correct itself at some point in time. And we'll see sea level rising along our coast more like it's rising elsewhere. Now, I don't really go along with that, but that's the argument that was really strongly put forth. And so that's one part of this NAS report that I don't think I think there's one place in there, I'll have to look, but that they do talk about this, but they certainly don't make it a big issue. They tend to downplay it. It doesn't take front and center by a long shot, and I think it should have had a lot more emphasis than it received. Bill?
Yeah, with regard to this map, has anyone actually calculated the averages of the lows and the highs?
Well, if you average all this, then you get the global rate, you'll get what those global average records were, and you'll get the global increase in sea level rise, which right now today is somewhat close to 3 millimeters per year. That's what you would get if you averaged all that out and smoothed it out and came up with a single number. At least that's what we'd like to think we'd get. That's what we should get, theoretically. Because overall, sea level is rising. I mean, everything indicates that. But it's just what's happening regionally that really gets complicated. And when you use these AOGCMs and you look at them regionally, because they do give you distributions of sea level rise around the planet, you find they all disagree. And so the picture even gets murkier when you try to use these GCMs and the AOGCMs to look at regional sea level rise. It's a real problem. They don't do well on regional sea level rise at all, and that's pretty well known.
It's the tennis shoes.
Tennis shoes?
The tennis shoes.
Yeah. Well, there's got to be a few more questions. Yes?
So you spoke a little bit about the reservoirs and freshwater, human use of freshwater.
Right.
And that affecting sea level rise. But then you briefly said there was an equilibrium, and I missed that.
I'm not saying it's an equilibrium. I'm saying for the purposes of this report, the committee decided that we would assume that the sources and sinks of fresh water on land tended to balance out, so that terrestrial storage was essentially a non-issue. It was zero as far as the calculations were concerned in our report. Now, I haven't spent a lot of time on this, but a lot of people are now working on terrestrial storage specifically because it is so poorly known that the numbers that you read in the literature vary so widely, you don't know what to believe. And so it seemed like an easy way out for the report just to simply say, okay, we'll assume that the plus and minuses all tend to cancel and we got no effect. Well, that's kind of a cop-out, but that's the best we could do given the circumstances. You had a question?
I did. As far as the local, not rising along our coast, was there any arguments that your colleagues put out about why this trend, this negative trend would stop and it would start to rise? That's what I've always been confused about with this talk is like, why would it start to rise here if it's not? I mean, what are people arguing?
Well, actually, it depends on the arguments that we've given that favor feedback processes. If they're in any way correct, we'll maintain what we have. I don't see that it will turn around. But like I say, that bucks conventional wisdom. I put the word wisdom in quotes here because a lot of the people who are working on this problem think that things will change along our coast. This is temporary. But when I look at the details and the arguments, I don't see how that's going to happen. But maybe it will. I don't know. See, one of the arguments would be this. Part of what we're looking at is strictly the thermal expansion component. Now, if we look at the cryospheric contribution, that comes from the poles. It comes from the South Pole, not too much from the South Pole yet, but we get a lot of input from the North Pole, from Greenland in particular, Alaska, and other ice sheets and so forth from Canada. Now, that fresh water can work its way down to lower latitudes and certainly impact our region. And so given enough time, the actual cryospheric contribution to sea level rise could actually become very important and change this whole picture. Even though the processes that we're talking about are still working, they're being bombarded with fresh water coming in from other locations, and eventually that tends to dominate the picture. And that's how it could actually turn out. But so far, we haven't seen that. So, I don't know. We've lost Erica. Erica, where are you?
No, she's not.
Oh.
And Erica asked me if there are no further questions, we have to thank Larry. Make sure to tell you that he will stay here a few more minutes and entertain personal questions